Welcome back to the deep dive. Today we are stripping everything down to the bare circuit board.
Oh, literally.
Literally. We are looking at a stack of research that honestly feels a little bit like science fiction, but not the shiny, chrome-plated kind you see in movies.
No, this is the garage level sci-fi, the kind that happens amidst the smell of soldering smoke with parts you scavenge from the bottom of a drawer.
Exactly. We're exploring the work of a creator who goes by the name Bobricius.
And just calling him a creator or a maker, it really feels like a massive undersell. What we're looking at today is a case study in a very specific, I'd almost say radical engineering philosophy.
It is. It's about rethinking how computers are actually physically built.
From the ground up.
It really is.
Yeah.
I've been reading through his logs on Hackaday, browsing his Kindie store, and looking at the project notes he sent over. And the contrast between what he builds and what the rest of the tech world is building is, it's jarring.
It is.
You look at the phone in your pocket right now or the laptop on your desk, everything is sleek, everything is sealed shut. It's black box engineering. If you want to use an AI, you send your data to some server farm in the desert.
And if you want to send a text, it bounces off a satellite. It's a system built entirely on dependency. We rely on the cloud, we rely on the grid, we rely on manufacturers to keep everything running.
But Bobricius, his real name is Peter Mazenko, is doing the exact opposite.
Yeah.
He's building what I've seen described in some of these articles as doomsday tech, which sounds a bit dramatic.
It does sound dramatic, though. I think resilient infrastructure might be the more academic term.
Yes, that's it. But doomsday kind of captures the stakes, you know.
It does. We are talking about computers so small they fit on your keychain,
Yeah.
devices that can run indefinitely on harvested solar power, and communicators that let you chat wirelessly with your neighbors when the entire internet has collapsed.
And that's the hook for me. That is the aha moment. Imagine a world where the power's out, the cell towers are dead, but you can still send a message or run a computer program because your device doesn't need any of that external support.
That's the mission of this deep dive, to explore how this one engineer is, well, fighting back against the touchscreen era and the cloud data harvest.
He's building devices that put control back in the user's hands,
Uh-huh.
literally and figuratively.
Right.
So we have a lot to cover. We're going to look at how he takes these raw circuit boards and turns them into robots and art pieces and privacy tools. But before we get into the heavy engineering, we have to talk about the name. Bobricius. It sounds like a Roman general who commands a legion of soldering irons. Hail Bobricius.
It does have that imperial weight, doesn't it? It sounds so authoritative. But the origin is actually much more grounded, much more humble.
Yeah, I found this anecdote really charming. The story goes that it started at a summer camp way back when. There were two kids named Peter.
A classic problem.
Standard logistical nightmare for the counselors. So to distinguish between them, Masenko was given the nickname Bobor.
Which is Slovak for beaver.
A beaver, which, if you sit with that for a second, is actually the perfect mascot for an engineer.
It fits perfectly. Think about what a beaver does. It is the engineer of the natural world. It builds dams, it creates infrastructure.
It changes the entire landscape using only the mud and sticks it finds right there.
Exactly. It is earthy, practical, and just incredibly industrious.
But he didn't stay Bobor. Over time, that nickname evolved. It became Bobricius. And he says in one of his interviews that it's meant to be a Roman emperor-style name, something like Magnus Deus.
And that evolution, that shift from Bobor to Bobricius, it actually captures the duality of his work that we're going to see throughout this deep dive.
So,
Well, on one side, you have the beaver, the scavenger, the guy using scrap parts, the humble soldering kits, the earthy practicality. But on the other side, you have the emperor, this grand, ambitious design philosophy that wants to conquer the problems of modern technology.
so it's high art meets survivalism.
Precisely.
Okay, so let's unpack the beaver side of things first. The raw engineering. Specifically, his approach to the PCB, the printed circuit board.
Right.
I think for most of us, if we even know what a PCB is, it's just that green board inside the computer that we never see.
It's just the thing that holds other things. In traditional manufacturing, the PCB is a chassis. It's a carrier. You treat it like a dinner plate. You just pile the food, which is the chips, the capacitors, the resistors, on top of it.
The plate itself isn't the meal.
Exactly. It's just there to hold the meal. But Masenko looks at the plate and says, no, this is part of the meal.
I like that analogy.
He believes the PCB shouldn't just be a passive holder for chips. It can be the device itself. One of the best entry points to this idea is one of his early viral hits, the Picaduino.
Okay, I'm looking at the specs here. 12 by 23 millimeters. That is That's smaller than a postage stamp. It's barely the size of a fingernail.
It is unbelievably tiny. He built it around the 1885 microcontroller.
Okay, break that down for us. What's the 1885?
So it's an 8-bit AVR microcontroller. Think of it as a very weak, very cheap, but very, very tough little brain. It doesn't have much memory. We're talking bytes, not gigabytes, but it's easy to program.
A favorite in the maker
A
community.
huge favorite. The DigiSpark, which was a small development board using this chip, was everywhere. Misenko looked at the DigiSpark and thought, I can make this smaller, and I can make it smarter.
Usually when you make tech smaller, you lose features. You lose ports, you lose buttons, you lose the ability to actually do anything with it.
Exactly right. In the Arduino world, if you want to drive a motor or light up a fancy LED, you usually need what's called a shield.
A second board you stack on top.
Right. It's like a sandwich. One board is the brain. The other board handles the power or the specific task. It's the muscle.
So you have a brain board and then a muscle board on top.
Yeah.
And suddenly your tiny little project is 2 inches tall and kind of wobbly.
Right. But Misenko's philosophy was that you don't need shields if you design the PCB correctly from the start. On that fingernail-sized Picoduino, he integrated the motor driver and the RGB LED directly onto the main board.
How? I mean, where did he find the space?
He routed the copper traces so efficiently that he didn't need the second layer. He collapsed the stack.
He eliminated the stack.
He eliminated it. It's like fitting a Swiss Army knife inside a matchbox.
Oh.
It proved that you don't need these add-ons to do something powerful. But where he really pushes this PCB as component philosophy into the realm of, well, physics, and this is the part that blew my mind, is with his moving circuit boards.
Okay, this was the part of the research where I had to stop and reread the notes 3 times.
Rare.
When I think of a circuit board, I think of a rigid, static object. It sits there.
Yeah.
It does not move.
Right.
But he made a magnetic 2D motor out of the board itself.
Yes. This moves from just clever packaging to inventive physics.
Yeah.
He created a planar stepper motor using nothing but the PCB.
Okay, you have to walk me through the physics here. How do you make a flat piece of fiberglass and copper move something?
Okay, well, think about how a normal electric motor works. You have a coil of copper wire wrapped around a core, right?
Right.
You run electricity through it. It creates a magnetic field, and that field pushes or pulls against a permanent magnet to create spin.
Electromagnets 101. Current creates magnetism.
So a PCB is covered in these thin copper traces. Usually those traces just carry signals from point A to point B in a straight line. But Misenko realized that if you arrange those traces in a spiral pattern, a very distinct geometric coil directly on the board's layers,
They become the coil.
the board itself becomes the electromagnet.
Right.
He designed these spiral coils right into the PCB layers. By manipulating the current flowing through those flat spirals, he creates a magnetic field that rises right out of the surface of the board.
So if you put a little magnet on top of it.
You can push and pull that magnet. He can move objects in 2 dimensions across the surface of the board just by changing which copper spirals are active at any given moment.
It's unbelievably elegant. He didn't just connect the brain to the muscle. He made them out of the same piece of fiberglass.
The boundary is gone. They are the same object. And he doesn't stop at pure function. He really leans into the aesthetics of it all. You see this in his cyberdecks and his art pieces.
Oh, I saw the pictures of the Star Trek Enterprise he built.
Isn't that incredible?
It's beautiful. It's all black and gold. And the components, the LEDs, they light up the nacelles. It doesn't look like a circuit board. It looks like a prop from the movie.
His whole goal is to prove that electronics can be visually striking. He calls it artistic PCB design. He's stripping away the plastic case and saying, look at the beauty of the traces, look at the geometry of the silicon itself.
It's like the trend in industrial architecture where they leave the ventilation ducts and the pipes exposed, but for microchips.
That's a great way to put it. And that aesthetic of exposed functionality, of seeing exactly what the machine is and how it works, that leads directly into his war against the modern interface.
The glass slab.
The touch screen.
We all know this feeling. You're trying to type a long email on your phone, your thumbs are cramping up, you're hitting the wrong keys because there's no feedback. It's just flat. It's cold glass.
It is a sensory deprivation tank for your fingers. Misenko calls this glass slab fatigue. As touchscreens took over, we gained this infinite flexibility. The screen can be a keyboard or a video player or a game controller, but we lost something.
The efficiency.
Yeah.
And the joy. I miss the click. I really do. There's something so satisfying about a button that actually travels downward when you press it.
You aren't alone. And this frustration, combined with a very specific global event, triggered his next big phase of creation.
You're talking about the chip shortage.
The global supply chain collapsed during the pandemic. You couldn't get high-end chips for love nor money. The factories were stalled. But interestingly, right in the middle of all this, the Raspberry Pi Foundation released their Raspberry Pi Pico.
And it features the RP2040 chip.
Right. And we need to pause on the RP2040. This specific chip is so important to the rest of this story.
Why? What made it so special?
It was a game changer. For one, it was available, but it's also a dual-core ARM processor. It's incredibly cheap, like $4 or $5, and it has this killer feature called PIO. Programmable Input-Output.
Okay, in plain English.
It means the chip is unbelievably flexible. You can program the pins to speak almost any data language you want very, very fast without bogging down the main processor cores. It was the right chip at the right time. So Masenko takes this cheap, available brain, and he builds the Pi computer.
The Pi computer. It sounds like something from the 80s, but it's totally modern.
It is, and it's a platform. This is a distinction I want to make sure we really nail down. He didn't build 3 different machines. He built one single hardware shell, the Pi computer, that changes its entire identity based purely on the software you load into it.
One hardware, multiple purposes.
Correct. Imagine a device that looks kind of like a Game Boy, but with a proper clicky, QWERTY keyboard and a nice, crisp IPS display. You hold this one object in your hands, but it can be 3 completely different things depending on what SD card you put in.
Okay, so I'm holding this device. Talk me through it. Identity number 1, Armachat.
Armachat is the survivalist identity. This uses LoRa radio technology.
LoRa, that's L-O-R-A.
It stands for long range. Most of our wireless tech Wi-Fi Bluetooth operates at 2.4 gigahertz or even higher. High frequency means you can send lots of data, like Netflix streams, but the signal is weak. It gets blocked by walls. It fades after a few hundred feet.
Right, my Wi-Fi barely reaches the backyard. If I walk down the street, forget about it, it's gone.
LoRa operates at a much lower frequency, usually around 433 megahertz or 915 megahertz. These radio waves are physically longer. They travel further. They can punch through buildings. They can even travel over hills.
So this is the doomsday communicator.
This is it. If the grid goes down, if the internet is scrubbed, if the cell towers lose power, 2 people with Armachats can still text each other over kilometers. It is completely 100% off-grid. Masenko's motto for it is, my network, my rules.
That is incredibly appealing in a world that feels increasingly fragile. It's independent comms. But then, okay, say the world isn't ending. It's a Tuesday, and I just want to relax. I can swap the software, and boom.
Identity number 2, PICO-ZX.
Ah, the nostalgia trip.
Now we're in the realm of pure nostalgia. The PICO-VX is an emulator for the classic ZX Spectrum computer.
The 8-bit legend from the UK.
The very same. So now this rugged survival tool is a handheld gaming console. You can play Manic Miner, you can write code in BASIC. It brings back that tactile experience of the 1980s. And again, because of that powerful RP2040 chip, the emulation is flawless.
And then there's a third one, right?
Identity number 3, MCUME, which is a multi-platform emulator. So now you're playing Commodore 64, Atari, various other classic consoles.
What I love about this is the respect for the user.
Yeah.
Apple sells me an iPhone, and it's an iPhone. That's it. I can't easily turn it into a long-range walkie-talkie. I can't really reprogram the operating system. It is what they say it is.
Right. Apple wants you to be a consumer. Bobricius wants you to be an operator. By standardizing the shell, the screen, the keyboard, the processor, he creates an ecosystem where you decide, is this a toy today or is this a lifeline?
It empowers the user to define the technology rather than the technology defining the user, which brings us to the present day. We've covered the hardware, we've covered the comms, but now we have to talk about the absolute cutting edge, the elephant in the room.
Artificial intelligence.
Exactly. Masenko looks at ChatGPT, he looks at Claude, and he sees a problem.
He sees a privacy nightmare. And let's be honest, he's not wrong. Every single time you ask a chatbot a question, that data leaves your device. It travels to a corporate server, it is processed, stored, and potentially used to train future models.
We are feeding the beast with our own thoughts.
We are. So Bobricius decides to build a local AI in your pocket.
Enter the ZPR.
A ZPR AI terminal, ZEPIR.
Now, the name relates to the Raspberry Pi Zero, which often acts as the brain here, but it also stands for something else, doesn't it? Zero component.
This is the deep dive moment. We really need to explain zero component because it sounds like marketing fluff, but it is actually an astonishing engineering flex. It's really, really difficult to pull off.
Okay, let's unpack this. Usually if I want to connect a screen and a keyboard to a computer chip, I can't just wire them straight in, can I?
Generally, no. You need translators. You need a dedicated microcontroller just to handle the keyboard matrix scanning to figure out which row and column is being pressed. You need a driver chip for the display to interpret the video signal. You need a digital to analog converter for the audio. You have a whole chain of intermediate components.
It's like a bureaucracy of chips. The CEO, which is the CPU, talks to a manager, who then talks to the worker.
And Misenko basically said, fire the middle management. He got rid of every single one of those intermediate chips. He utilized all 40 pins of the GPIO.
The GPIO, just remind us.
The general purpose input-output connector on the Raspberry Pi, the programmable pins. He connected the matrix keyboard, the SPI display, and the audio output directly to the Pi's processor pins.
Direct wiring. But wait, if you remove the hardware that usually handles the boring stuff, like constantly refreshing the screen or scanning for key presses, doesn't that mean the main brain has to do all that work now?
Yes, that is the catch. When you remove the helper hardware, the software has to take over the entire job.
So the main brain is now doing all this heavy lifting for absolutely everything.
It's incredibly difficult to do. It requires precise kernel hacking. The Linux kernel, the core of the operating system, has to be told how to drive the display directly, pixel by pixel. A separate Python script has to run constantly, scanning the keyboard matrix thousands of times a second, just to see if you've pressed A or B.
Okay, so why do it this way? It sounds like he made his life strictly harder. Was he just showing off?
Well, partly, maybe. It's definitely a look what I can do moment. But it was born of necessity. Remember the chip shortage? If you can't buy the display driver chips because they're out of stock globally, you have to design around them. You have to find another way.
So necessity really was the mother of invention here.
It was. But the result is a design of pure efficiency. It reduces cost, it reduces complexity in the supply chain, and it reduces the number of failure points.
If the driver chip isn't there, the driver chip can't break.
Exactly. It is minimalist engineering at its absolute peak.
So what can the ZPR actually do? Because if it's just a stripped-down terminal, can it actually run a proper AI? I mean, LLMs are heavy. They need a lot of power.
It is a powerhouse. The ZPR board itself is a carrier. When you plug a Raspberry Pi 5, which is the newest, most powerful version, into the ZPR, it has enough RAM and processing grunt to run local large language models. We're talking about capable models like Qwen 3 or 5.4 Mini.
Wait, so the AI is running on the silicon in my hand, not on a server somewhere.
Entirely. You could be in a submarine or in a bunker or just in the middle of the woods with no signal. You type a prompt, and the Pi 5 generates the answer locally. No internet connection required.
That is huge. That changes the dynamic completely.
It supports voice features too, speech recognition and text-to-speech, and it's all happening locally. Plus, it's a full Linux terminal. You can use Git for your code. You can program in Python. You can manage your files. It's a real computer.
And the why here is privacy. 100%.
Absolute privacy. Your conversations with the AI never leave the device. There is no data harvesting. There are no subscriptions. It is a closed loop. In a world where the saying is, if the product is free, you are the product, the ZPR is a declaration of independence.
It connects back to that doomsday vibe, but in a digital sense. It's not just about surviving a nuclear winter, it's about surviving surveillance capitalism.
It is digital sovereignty. And frankly, just on a practical level, having an AI assistant that works when the Wi-Fi is down is just incredibly useful. How many times have you tried to ask Siri or Google something and it says something went wrong just because you had one bar of signal?
Too many times to count. It turns a smart device into a dumb brick.
Exactly. ZPR never becomes a brick.
True. But all this tech needs power. And if we're talking about true resilience, if we're talking about the zombie apocalypse scenario we keep joking about, we can't be hunting for a wall outlet every 4 hours.
Which brings us to the fourth pillar of the Bobricius philosophy, energy harvesting.
The quest for the infinite battery.
Misenko is obsessed with this. He has created these amazing little LED watches that use photodiodes, not just to detect light, but to generate power.
Wait, pause there. I thought LEDs use power to make light. That's their whole job.
They do. But physics is often wonderfully reversible. An LED is a light-emitting diode, but if you shine a bright light onto an LED, it acts like a tiny solar panel. It generates a small voltage.
No way. You're kidding me.
It's not much, I'll grant you. You aren't going to power a toaster with it.
Yeah.
But for a tiny, low-powered digital watch that sleeps most of the time, it's enough. He builds these watches that literally charge themselves from the ambient light in the room.
So they run indefinitely without a battery replacement.
Indefinitely. It's clever, isn't it? It's using the component for two things at once, display and power source.
That's brilliant.
He's also built supercapacitor lamps. Supercapacitors charge almost instantly and can last for millions of cycles, unlike chemical batteries which degrade over time and with each charge.
But one of his most interesting niche tools, I thought, was the coin cell emulator. I saw a picture of this. It just looks like a little fake battery.
Exactly what it is. Think about how many devices you have that use those little CR2032 coin cells. Your car key, your TV remote, your kitchen scale, maybe your guitar tuner.
And they die. You throw them away. It's so wasteful.
And they are always dead right when you need them most. Masenko built a small PCB that is shaped exactly like a coin battery. But instead of chemicals inside, it has a tiny voltage regulator and a connector. You pop it in, and now you can power that device from a rechargeable lithium pack or even a USB line.
It's such a small thing, but it attacks the whole culture of disposable tech.
And it fits into the broader ecosystem he's building. If you step back and look at the whole picture, he is building a triad of independence.
Right. Let's put it all together. The big picture.
Okay, so you have ArmaChat for communication talking without the grid. You have ZPR for computation and intelligence thinking without the cloud. And you have his energy harvesting projects for power running without the outlet.
It's a complete survival kit for the digital age.
It is. And crucially, it is accessible. He uses open source tools. He designs these things so that other people can build them. He sells the boards on Tindi, sure, but he also shares all the code and the schematics online.
He isn't gatekeeping this resilience. He is distributing it.
Exactly. I think that's what separates him from a commercial company. Apple wants you to buy the iPhone 16. Bobricius wants you to learn how to solder.
He wants you to understand the machine you're holding. He wants you to look at the PCB and see this city map of electrons, not just a black box of magic.
Right.
So as we wrap this up, let's look back at the big picture. We've talked about these Bobricius principles.
I think there are really 6 pillars here when you boil it all down. Minimalist, accessible, resilient, artistic, practical, and maybe most importantly, privacy-focused.
It's a transition from being just a maker, someone who tinkers in a shed for fun, to creating what you called resilient infrastructure for the individual.
I think that is the key takeaway. Modern technology is amazing. I love my smartphone. I love streaming video, but it is fundamentally fragile. It relies on global supply chains, massive server farms, vast energy grids, and stable internet connections. If any single link in that very long chain breaks, the phone in your hand becomes a very expensive glass brick.
And Bobricius is reminding us that we can build technology that is robust. We can do more with less.
Zero component. That philosophy, doing more with less, isn't just a way to save money or be clever. It is a survival strategy. It is about understanding that if you strip away the bloat, the tracking, and the dependency, you are left with something purer and, in many ways, more powerful.
It really makes you look at your smartphone differently. It feels like a leash sometimes. The ZBLEP feels like a tool.
A tool that belongs to you and only you.
So here's our final thought for you to chew on today. We live in a world where our devices are increasingly becoming dumb terminals for smart cloud AI. Your phone is really just a window into Google's brain or OpenAI's brain.
Which begs the question.
How much true computing power do you actually hold in your hand right now? And what happens to your digital life if the internet simply turned off tomorrow, if the fiber lines were cut? Does it all just vanish, or does some of it stay in your pocket?
Bobricius suggests that we might want to keep a ZPR in that pocket.
Just in case. Thanks for diving in with us. We'll see you next time.